let's see if we can move a little forward, because the reason I was diving a bit more deeper into this is to just actually get the whole thing fixed, right? So because I was running the thing, and basically when I run the thing, basically the whole thing, the cost function doesn't really get updated, right? So this is the this is the forward pass. In a way, you can just say like, well, why the output is equal softmax, and then essentially have Z2, which is basically the dot product between A1, W2, plus B2, correct? And then obviously A1 is, here's an activation function, NP tangent of Z1, and then obviously Z1 is in of itself NP dot XW1 B1, right? I'm missing some parentheses probably somewhere. That's the tangent. That's this. It's too much. One too many. Right. So that's why, like, this is kind of the whole function we're computing, right? That's why we essentially want to derivate these. Right. Now we have to take into account, so we just have to treat W1, W2, like these are all variables, right? B1, B2, right? So we might as well call them like X, Y, Z, and whatever it is, right? Now what we wanna do when we do the backpropagation is say, I mean, you could even just, it seems like, I mean, softmax is just an activation function. For some reason, they keep that aside in some cases, right? And they just kind of like, that's fine. Okay, we can just, because we could, in theory, to keep this easier, kind of like ignore this in terms of calculating the derivatives. And so that is essentially, right, like it's a big composition. So to calculate the derivative of these things with respect to W2, well, no. Yes and no. No. What you're doing is you're calculating not the loss of these, but you're calculating the loss. You're calculating. That's your function, but you're calculating. You're calculating the derivative of the loss function, right? With respect to these. So we have this output function, or we have this null network. Where W1, W2 are the weights of the layers. Okay. The two layers. going to explain basically gradient descent step by step, right? So I have the y function, and I'll compute the loss. And backwards propagation is the aim is to know how much each parameter has contributed to the loss. We compute gradients of partial derivatives of the loss function with respect to each parameter of the loss function, right? Chat. That's actually a good. That's probably docs. I'm curious. That's a good answer. It seems like a good answer so far. Much each parameter has contributed to the loss. We compute gradients or partial derivatives of the loss function with respect to each parameter. Of the loss function, right? Cross-entropy loss. Okay, so that's kind of like what we're assuming here. Yeah, but cross-entropy, so what count step by step. Cross-entropy loss or so I'm not gonna not explain code. Can I not stop the generation? Chat. Cross entropy is then a function of y, right? It's a function of these. Yeah, exactly. Y comes into play. Chat. So actually, it keeps the original. Oh no, it doesn't keep it. It replaces it. So you're working with this stuff, bunch of inputs at a time, but reducing it to exactly. Let's pretend our for preparation data as output, but the true output is 001. Oh, that's actually a very good answer. Yeah. Well, at least I like the fun. So for propagation, so compute cross-entropy loss. For example, this propagation. Here we compute Z2, which could be the derivative of the loss with respect to the final output before activation. Before activation, okay. Cross-entropy combined with softmax gives relatively simple derivative. Okay, this we'll dig into this later, but yeah, this is basically what we have. Okay, that's kind of what I was trying to do with my example. And then apply chain rule. Next, we have to figure out how much it's Z2, which could be the derivative of the loss with respect to the final output. I mean, why is that even the first step? It's not really explained here, but I assume this is just because you're going to need it for the final formula, right? Apply the chain rule. Next, we have to figure out how much our loss would change if we tweak W2 parameters known as dW2. So here we take the derivative of Z. Here we take the derivative of Z W2 with respect to W2. Why? Why? So, why the derivative of Z2? Compute Z2, which could be the derivative of the loss with respect to the final output. You know why? Okay, so in step 4, why do we need to compute the derivative of Z2 in order to obtain dW2? Like, Z2 is the derivative of the loss already. Z2. You know what I mean? Like, it is too much prescriptive without explaining. Like Z2 is this. I get it. That's where W2 is. That's the main parameter, right? But we're optimizing the loss function. Why not? So in step 4, the code, there's no such code, right? Explain code. I don't want to explain code. It would be good if it kept the mode. I can choose the mode up front. We do indeed need derivative of the loss function with respect to the weights. But obtaining these directly can be quite complicated due to the complex nature of the function. It involves nested functions, including softmax activation, linear transformations, and the loss function, etc. By using the chain rule from calculus, we break down this computation into parts. We first compute the derivative of the loss with respect to. So we first compute the derivative of the loss with respect to the output of the final layer before activation. So dz2. Since this is the derivative of the loss function with respect to z2. But again, that's not the derivative, as in that is a constant. It's a constant. That's what I don't understand, right? So if we're doing this, we have a clear result. That's not. It's an evaluated derivative. That's what's bothering me with this. But okay, next we compute dw2, the derivative of the loss function, by taking the dot product of the derivative of the two and the transpose situation out in the previous layer. This gives us the rate of change of the loss function for the change in our weights. So, okay, yeah, we're doing it step by step. I get it. I get it and I don't get it. Let's say, can you remind me formula chain rule. So if it's a function that is like y of u of x, and you want to make the derivative of y with respect to x, either the derivative of y with respect to u, no, no, times give me function. Okay, so then it will be f of u is u squared, and then yeah. So the derivative with respect to u. So first you kind of abstract that away, and then you kind of plug that in. No, or what? It's 2 times u, obviously, and then d dx is 3, and so basically what we're saying here is, in this case, is 2 times 2u times 3. Okay. It's all the time. It's essentially all the time the derivative. It's essentially all the time the derivative of this big thing, right? So okay, before activation. So let's forget activation. So we have this stuff here, right? And again, if we want to simplify that, so we don't have this dots and whatnot, right? This is essentially times w1. So that's sort of plus b1. That is one thing, right? And then essentially, I don't know what to do with this tangent thing here. Whether we keep it or we don't keep it, probably be done. But that's kind of essentially saying w2, you know, and then kind of thing plus b2, right? So that would be kind of the simplification. But in a way, you know, this is kind of, let's say, z1, right? So that's kind of like, that is basically z1, right? And so essentially what you're saying is the derivative of these with respect to w2 is obviously just z1. You can call it a1, right? Call it a1. Yeah. But let's take that into account, right? It's just a1. I think that's here. But again, that's not the point. The point is we're doing the loss function. Oh, entropy. So no, so let's assume that's so that's kind of that's kind of like y. That's like a way to simplify y, right? That's a way to simplify y. But then the loss function, the formula for cross entropy, so that is class classification. But then what's the derivative of these, you know? Y true, Y pred. What's bothering me here is I don't see where the loss function is, right? Again, we're doing the derivative of the loss function, right? With respect to, and the loss function is going to have these y, right? Give me code. Command entropy loss is derivative. So the cross entropy loss, and you have y true, right? The n samples. Cross entropy loss, it's basically the negative sum of NP, and then you have to do the logarithm of the predicted times true. And then you have the derivative. You have the derivative. And so you basically you give it, you know, y pred is basically the formula you have, right? So you give it that, and it will calculate your number. So in this case, you give it okay, but that's like the derivative with respect to, that's not, that's what's we're you know, I'm kind of like so lost right now. so lost right now. So you're doing, so you have these, right? I want to calculate the derivative of, I'm going to calculate the derivative of, and maybe it helps not to think in tensors, it helps to just think in like integer inputs and variables, right? I want to calculate the loss function of cross entropy with relation to W2. That is, this is my variable, okay? This is my x. So I have this here. So this is my function, my x. Derivative in this case, yeah, but this is y, right? I still need to plug this. I need to plug this in. I need to plug this in, because if I have the derivative with respect to a variable and then I instantiate that variable, that result is going to tell me the changes I have to make to that variable, right? It's telling me, yeah, exactly. So it's telling me what's the growth or what's the rate of change in that in given that input, right? So y doesn't simplify to these, right? I guess that's what I'm trying to get. So I have this function, right? But then cross entropy, if I take the derivative of cross entropy, this is odd because this does not include any derivative of y, right? So what's the cross entropy? So what's the cross entropy formula? Is LaTeX explain? Is it able to do that? The LaTeX? No. Okay. Give me the code, pseudocode. Okay, but that's what bothers me about this is that it has two variables. It has the predicted and the true values. It has our function, right? It has our function. That's exactly, that's what's bothering me, right? So it has our function. It has the true values. The true values are, because and these are kind of paired, right? Because it's how do how do we even approach derivation of these when it has the predicted y prime. How do we handle y true? Not code, but I want to ask. How do we even approach derivation of these? Right, I get it. That's how I calculate the entropy. As something that is a function. Well, a loss function is always going to have. A loss function is always going to have these two things, right? So the two variables, right? We have calculus, yeah, sure. So I guess you treat y true as a constant. The derivative. We know that the derivative of log x is 1 divided by x. This is 1 divided by y pred. Fine. Applying the chain rule. Okay, yeah, that's that doesn't solve my question, right? I'm saying how are we coming to these? How are we coming to these? How are we coming to these a1 times dz2, right? Is this with respect to the v2 that we're is it that we're just saying no? What? Yeah. Well, these. I'm lost. I'm lost. I'm actually pretty much lost. I'm like running in circles. We have y, right? So that's kind of like the composition of all the stuff in here. Again, I'm not. This is not. I'm just. These are just notes, right? So I'm not trying to kind of build any specific code in here. But that's. Yeah. This is a thing, right? Then our loss function is cross-entropy loss. If cross-entropy loss is the derivative with respect to with respect to y pred is this somehow. It's the derivative with respect to y pred is this somehow. But I want to know the derivative with respect to W2, right? How do I do this by hand? and what would be derivative of the derivative? The derivative. Yeah, I have the right thing. I just didn't know how to. How does this simplify to y prime minus y? Was it like that it simplifies to code? We don't want code. We want chat. We want chat. Chat. Worth to know that the simplification of y prime minus y true is specific to the case where y pred is passed through a softmax function. Okay. And the loss is calculated using cross-entropy. Okay, that's because of softmax. Okay. Probabilities. Okay. That's just because of softmax. Okay, fine. Oh, but we can work off of that. Can we? How do we work out the derivative with respect to W2 from there? Explain code, I want chat. I should be able to set the default. It seems to be bad at trying to figure out what mode am I really willing to use. So we already have the DL sort of the with respect to the output. And Z2 itself is a product of A1 and W2. So this is a derivative of Z2, right? So we're now trying to get the derivative with respect to W2. And here what they're claiming is that this is the derivative of by the chain rule, right? Okay. This is a simplification. Again, we're working off of the simplification because that's what softmax allows you, but that's kind of something else I have to work out too. Z2 is given Fine, that's fine. But let's just focus on this for a bit. So the derivative of the loss with respect to z1 to z2 is this one. Okay, z2 is like before softmax. Oh no, no! What happened? It's my internet's so bad. If I remember what wasn't there. There was that the derivative. Ah, come on, I should be able to figure that out by myself. Come on. Oh, it loaded again. Hopefully I didn't lose the stuff that I had here. So we already have the derivative of the loss with respect to z2 is simplified to this because of softmax. Okay. What do we mean hence by chain rule? The delivery of the loss with respect to W2. It's the derivative of the loss with respect to let's think about this for a second, okay? So can we say basically that Z2 is Y, right? But then Y, so but Y is all this stuff in here, right? So Z2 is a function of W2 equals to these. The loss function, that's what I was saying. The loss function is a function of Z2. And Z2 is a function of W2. So essentially, you kind of have the composite function of like, of kind of like, of Z2 W2, right? In a way. Okay. Yes. I think that's what I was saying. I think that's what I kind of abstract away from the specific of what the loss function is, because essentially, if you want to calculate the derivative of the loss with respect to W2, what the chain rule says is these, right? Is that you should calculate the derivative. Yeah, that you should calculate the derivative of the loss with respect to Z2, which we have, and then times the derivative of Z2. Yes, okay, that's just what the chain rule says. We have to believe that. We can maybe do another session on why the chain, like sort of abstract why the chain rule actually works. My problem is sometimes it's just hard to move from, it's just hard to operate at the example space, right? So if you're just thinking about the example, then you get lost into what is what. But essentially that is the statement you're making, right? You want to calculate, regardless, the thing is you don't really care what the formula of the loss function is. That is just the truth, right? The derivative, if you want to calculate the derivative of with respect to W2, then you need to calculate these two derivatives, right? So this one we know, we have it because it's Y pred. And then the derivative of Z2 with respect to W2 is just basically take the formula of Z2. I get it. And you don't really care right here what is really A1 kind of made of, right? Like you're working you're working at you have an instantiation of A1, which is your random initialization of W1. That's what you're working off of, because you want a specific value. That's fine. Okay, I'm offline, but I think I can sleep now. I can sleep now with this. I think I can sleep now with this information. Can I sleep with this information? But the next one is, okay, the next session is going to be, why does the chain work? How do you derive the chain rule? Essentially, it's just it's telling you that the derivative of these is basically the derivative of this function with respect to z2 as a variable times the derivative of that thing in there. Okay, fair enough. I think I understand that, but there are two important things in here. Obviously, if we don't know how to make that simplification, that is, the pret minus the whatever, then then you would kind of actually have to work for something else. Like if you would ignore this, then you'll probably take that. Can I go upper? Oh yeah, I'm at it. Then you'll probably just take that function. You just take that, right? That's the derivative. That's the general derivative, and then yay, connection. But essentially, I think it's funny because it's like sometimes to understand something, you can't go, like you just can't stay at the example level. You know what I mean? Like I was trying to think about, like, oh, so but L is this specific function, right? It's like, no, just forget about these. That's kind of what the theory tells you, right? That's what the first principle tells you. It's like, this is how I calculate the rate of change of this nested stuff. You do it like this, and this we know, right? This we know because we don't need to know what happens there. We know that the derivative with respect to Z2 is that, like, we can have a value for that already because we know how to calculate that, assuming that Z2 is just like a variable, not a function, right? It's like a black box. But then when you open the black box, in order to actually do the W2 thing, then you kind of do this way. That's why you're doing it step by step. And then, essentially, if I now want to go deep and calculate Z1, it's kind of like another step, right? So that will be the next. That will be the next step, because then essentially that's what you get here. So that's why we had some sums in here and whatnot, didn't we? Okay. BW2. Still, I'm not so sure about these, but whatever. So this makes sense. This we have to think about. And then, interesting. But it's a similar idea, right? These are 2 times W2. Oh, but here's like a funky tangent stuff here. Yeah. Okay, we can work this out in the next session, definitely. This is the key. This is really the key. It's the fact that first you do basically the derivative of these is like you're treating it like a black box. So it's the derivative of this with respect to the black box times the derivative of the black box with respect to their input. Okay. That 2 is essentially something that is a function of, in this case, not Z1, right? But it's like tan x of Z1, right? That's kind of the trick here. That's why you get that's why you get that. That's why you get that thing that's a little more complicated. Because the derivative of tan is, I think I checked that before. Yeah, exactly. 1 minus, there you go. There you go. This is what you have. This is what you have in here. Yeah. This is what you have in here. Now I understand it. I don't know what happened. It's a weird phenomenon. I just don't know. I don't know. This is basic stuff, right? This means I knew the concepts before. But then somehow it's not just the refreshing of it, but it's like where did my thinking go lost? Like I think one problem was talking about functions and then thinking about the value of this of the function, right? Because we have in the case of a specific backward propagation path, we have one specific value for W1, for W2, for B1, for B2. And I think it was me trying to think of too much of like the specific of, okay, so what is cross entropy? So cross entropy is these minus these, blah, 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 blah. But then it's like, no, just forget about it. Actually, the specifics of the formula of the loss function, they're only needed for the first step, right? Because then when you get into because then just thanks to the chain rule, to calculate the rest of the stuff, you just need to dive, you can't ignore the loss function formula, because then you're just diving into the derivatives of each of the black boxes, which is the beauty of it, I guess. This is what makes it mathematically attractive and easy, because you just do these ones for the high level. And if you can find something that's simple enough, like in this case, y prime minus y true, then you're good. And I think my thinking was like, oh, but I need to plug in the loss function, I need to put these whole formula in there, then do the whole derivative of this big thing. That's my think. That I think that's where my thinking was wrong. It's just kind of, I don't know how to call this. This is, so my reasoning problem here was basically, I could just have stayed at the chain rule, right, and just accept that, and then dig into that in an isolated session, away from an example, or away from that example. But instead, I'm like, no, let's take the loss function. Let's replace the parameter y, right? The parameter with the actual formula, which is this whole thing here. And then now I need to calculate, the derivative with respect to like W2. But then that's why the chain rule was derived in the first place, to simplify the process. I guess I could do this, but then it would be complicated, right? Chain rule kind of makes it easier, because then you only have to worry about the loss function shape, or the loss function in of itself just once, and then each of the different boxes in it, because it's one big nested function. I guess that's it. In a way, I was not wrong. In a way, I was not wrong. It's like I was just putting the problem as is, right? I just knew chain rule is there at some point, but I just kind of kept ignoring it because I wanted to kind of understand the detail. But then that in the same time was like the problem, right? It's like, well, I have this problem, but then I just don't need to worry about it because I have the chain rule. I didn't know how to solve that very complicated derivative, where it's like, take take all these, treat that as a constant, plug in here the whole function, even with the softmax stuff in it. So that's still one thing. So that's still one thing to dive into, right? So why the softmax allow us to do this? you know, I would have to take this derivative and then replace this with a function and make the derivative of that with respect to W2. I mean, we could, you know, we could actually do this. Why not, right? But no, that's a cross-entropy derivative. That's wrong. I should actually take a look at these. You know, I should basically plug it in here and then do the whole derivative of these, right? So I should just take these, put in here the function, and say, well, we could, you know, which in a way we could try to do with SymPy, right? Can you give me? I don't know if it's gonna work. Maybe we could just to play with it, like, because let's assume let's assume that nobody had invented the chain rule, right? So you would typically approach that like this. You'd say, maybe that's that's an interesting thing to try for the next. Can we arrive? Okay, so let me just first of all. Of course, SymPy is going to use in the background like a chain rule or whatever, but like game challenge. Can we arrive? Same result starting off of a row formula like this, n, right? Because that's the formula, right? That's cross entropy. Yeah. Or whatever it is. And use SymPy W2. Because that's what I like. If I would approach a problem from scratch, right? I'm like, fine, I have this thing. I need to calculate the derivative of that stuff with respect to these. Like, you know, here because we know the chain rule, but I'm like, you know, in a world where I didn't know that, where that wouldn't have been sort of derived as an axiom, that is something you can apply as a, you know, mathematical rule. And if you have the tools like SymPy, right, you don't have to do it by hand. So you know the concept. You know to have to do the derivative of the loss function with respect to that stuff. This is just a simple way to to calculate it. So let's leave that challenge for the next session. Yeah. But then also want to know why the chain rule works at all, you know. So challenge 2, derive chain rule. Challenge 3, write the softmax simplification. Okay, I think this is a good thing to work on. That was a fruitful session. After meet.